This is part 2 of a 2-part video series on evaluating logistic regression models. Whereas we focused on concepts in part 1, we'll focus on the R code needed to implement these concepts in part 2. If you'd like to follow along with the code on your own machine, you can pause the video here to load the tidyverse and tidymodels packages, as well as the data used throughout this video. The Sydney dataset includes weather information on a sample of days in Sydney, Australia, including today's humidity and sunshine, and whether it rained tomorrow, that is, the next day. Our first goal is to build a logistic regression model of tomorrow's binary rain outcomes by today's humidity and sunshine levels. To this end, we can use the GLM function to fit the relationship between these variables using the Sydney data. Family equals binomial specifies that we're building a logistic, not normal regression model. And finally, we store the model results as rain model. Evaluating this model is a multi-step process. To begin, we can augment our weather data with information from the model. To this end, we apply the augment function to our rain model object, which happens to include information both about our model results and the data we used to build the model. Now, the results shown here seem a bit overwhelming, so let's narrow in on some familiar pieces. First, the columns highlighted here are just our original data points. This is our Sydney data. Further, the fitted column includes the probability of rain tomorrow as calculated by our model for each data point. For example, the first day in our dataset had a humidity of 92% with 0 hours of sunshine. Based on these two observations, our logistic regression model returned a 79.9% chance of rain, and it did in fact end up raining. This column, the fitted column, brings up an important piece of the code. By including type.predict equals response, we're communicating that we want this model uncertainty about the rain outcomes communicated on a probability scale. Now, if we leave this out, the fitted values would be communicated on the log odds scale, which is just a bit messier to work with. So we don't get overwhelmed by all the other information in this table, which I'm not going to talk about, let's select and just focus on 2 columns: rain tomorrow, whether it actually rained, and fitted, the probability it rained as calculated by the model. Recall that we often want to turn these probability calculations into binary yes or no, true or false predictions of rain. This can be achieved by the mutate line here. This line indicates that we want to define a new variable named predict rain, and we'll define the contents of this variable by comparing the probabilities in the fitted column to a threshold of 0.5. I'm using 0.5 as an example here, but again, this is something that you can change. This code represents our prediction rule then. If the probability of rain, fitted, is at least 0.5, predict rain, true, otherwise predict no rain, false. Let's check out the results for just 2 of our data points, the first and the last. For the first data point, the probability of rain was 0.799. And since this falls above the 0.5 threshold, we'll predict rain, true. For the 10th data point here, the probability of rain was only 0.11, and since this falls below the 0.5 thresholds, we predict it won't rain, false. We can similarly plug in true-false binary rain predictions for each data point. So for each data point in the dataset, we now have the actual rain tomorrow outcomes in the first column and binary model predictions of rain in the third column. To evaluate the accuracy of these predictions, we essentially want to compare these 2 columns. And as we learned in the previous video, we can summarize these comparisons in a confusion matrix. To obtain the information in this matrix, we need to count up the number of observations that fall into each category of actual versus predicted outcome. To that end, we can add the count function to our code. The results aren't in the same format as the confusion matrix, but they tell us the same information. First, the first row here counts up 3,119 true negatives. That is, for 3,119 days in the data set, it did not actually rain and the model correctly predicted no rain. The second row counts up 301 false positives, days on which it did not actually rain, but the model predicted it would. The third row counts up 563 false negatives, days on which it did actually rain, but the model predicted it wouldn't. And finally, the fourth row counts up 625 true positives, days on which it did actually rain and the model correctly predicted that it would. Let's pull this all together. Now that we understand this code a bit better, we can streamline it. First, as usual, we can build and store our rain model. Next, we can augment the observed data points with the fitted values or probability of rain calculations for the data points. Again, don't forget to specify type.predict equals response, or you'll get log odds instead of probability measurements. Finally, to make it easier to recall later, we'll store the results as rain model output. Next, we'll define a new column which obtains binary predictions of rain by comparing the fitted probabilities to a chosen threshold, 0.5 here. Finally, we can compare the actual rain tomorrow outcomes by our binary rain predictions using the count function. The results provide the same information as a confusion matrix, thus can be used to calculate the sensitivity, specificity, and accuracy of our model.